Okay, well, thank you very much for the introduction and indeed the invitation, Reinhard. I'm delighted to join you all here today with the subject very dear to my heart, neurorehabilitation. This title, Intelligent Robots for Rehabilitation, was given to me by Reinhard, and it allows me maybe to introduce some work that we're doing currently in UCD. I'm a physiotherapist, as Reinhard has said. I've worked for over 20 years, primarily in stroke rehabilitation, both here in Ireland and in the US. And more recently, I've worked in academia and research. So I'm delighted to present today some background, I guess, is around intelligent robots for rehabilitation. And is this science fiction or reality? We're seeing this real debate about artificial intelligence and are the robots going to take over? And certainly in the field of therapy, they're not taking over. They're a really valuable adjunct to physiotherapists. But I don't ever see a day where a robot will really replace the clinical reasoning and therapeutic handling that a good quality physiotherapist could provide. But today I want to talk in the talk today. Oh, I'm not moving on the screen here. I have a different screen to the rest of you in front of me.
Stop sharing for a second.
Okay, I'm getting some audio visual support here, thanks. Yeah, great. Okay, so that's lovely. So in the talk today, I just want to do a really quick, I'm preaching to the converted here, I think, so many of you are going to know this already, but a little bit on the current state of what we know about robotic gait devices, which is my particular interest. How do we make these devices more rehabilitative? That's one of the things I want to briefly discuss, and something that I really am very keen to move on in the field of robotics is how do we make these devices more responsive to the individual? Because that's what a therapist can do very instinctively. They know how much help to give, they know how to make a task challenging, and they know how to reduce the support as somebody's improving towards independence. So how do we make the devices more responsive? And will we see the day where you have a really intelligent device that will stand you up, walk you? As you get better, it'll reduce down the help you require, so you literally walk out of the device. That's my dream, that's my aspiration. It may not happen in my lifetime, but we need some preliminary steps to really understand this and to do it well. So just kind of a little bit by background of robotic devices in rehabilitation. Here, looking at spinal cord injury, on a systematic review, we see that there is evidence that they help to reduce spasticity in about 38% of people, and they improve bowel regularity in about 61% of users. There is a 3% incidence of bone fracture where people have been off their feet for prolonged periods of time and bone demineralization has occurred. So that's just a kind of a risk that one takes into consideration. Then when we move on to stroke, we probably have the strongest evidence here that in stroke, alongside physiotherapy, not in opposition to physiotherapy, it increases your odds. So your odds of walking independently are twice that of somebody who hasn't had robotic walking as part of their therapy after stroke. And the evidence really suggests that it is more effective in people who aren't mobile in the first place, and also that it's more effective early in the stroke journey. So the more acute, the better. Yet in this country, we don't have a robotic device in an acute hospital or in a rehabilitation hospital. They're all out in the community. And it might beg the question, are we intervening just that bit too late in the journey? And then when we look finally at acquired brain injury, there's very, very, very little evidence here in traumatic brain injury, for example. And there's really inconclusive evidence, but there is some evidence that is not that helpful in balance retraining. And that may be because you're not learning how to support yourself before you go on to do the movement. Now, just to say, I'm a fan of robotic devices before they ever move you, because they stand you up, okay? And this is the message the general population are really getting very strongly now, that sitting is the new smoking, that 8 hours of prolonged sitting per day increases your risks of multiple diseases like cancers, heart disease, stroke, diabetes, lung diseases, etc. But what I would say is that for most of us, being sedentary or having sedentary behaviors, it's a lifestyle choice for us. We have an option to change. We have an option to stand up. We're seeing public health messages encouraging to do it. But for many people with neurological conditions, this isn't a lifestyle choice. And this is where we need devices that help people to become vertical for their health. And that's before we ever start walking in the devices at all. So I like to start off with my 6 benefits of being upright. So here, what I call the 6 Bs. Being upright and weight bearing is good for bone health. It's good for bowel function. It's good for bladder function because of the gravitational effects. It's good for your overall hemodynamics and blood flow. It is good for your brain and your well-being. And it is also exceptionally good for the diaphragm in terms of optimization of the diaphragm anatomy, to allow the diaphragm to descend into the abdominal cavities. When you're sitting, you have abdominal content restricting diaphragmatic activity and causing, in some cases, atelectasis and collapse of the bases in the lungs. I won't get into this, but we have some nice evidence across stroke, spinal cord injury, MS, and other populations that standing alone increases ankle range of movement, it increases bowel, bladder, muscle function, etc. So standing alone is good. So then let's move on to thinking about walking while standing as an extra add-on here. And when it comes to devices, you'll see here a Locomat like we have over in the facility here. And then we have over ground walking device. I'm not sure if the video is going to come in here yet. So this is an over ground walking device. I like these because you have to initiate the walking. The walking doesn't come from a treadmill underfoot. You have to make the decision to step and walk. Because you can use robotic gait devices in 2 ways. You can have a passive passenger. So say in a complete spinal cord injury where the likelihood of restorative rehabilitation isn't an option, then this device will help people to stand and will help people to walk. And they'll be a passenger in the device. The device will do the work for them. We can also use it in that way to get people upright and to get people walking. But more recently, the devices have active assistance modes. So you can reduce down the help the device is giving and the person has to become more active in the walking. These are therapeutic parameters that the physio or other rehabilitationist sets. So you're making a judgment call of how much you think the person will or can do. And my 2 questions in really thinking about responsive and rehabilitative devices is, if the person is being active in the device, is the device doing what the person intended in the first place? And if it isn't, then they're giving a conflicting message. So you're developing a brain signal that says, I want to step and I want to step this way, and then an entirely different step to what you planned happened. Well, that's a conflict of feedback in the motor learning system, and that may not be helpful. So that is why I think if we had a really intelligent robot, it would understand what you want to do. It would understand what it is you can do and what it is you cannot do. And then it would only provide the minimal amount of help to require you to successfully complete the task. And all good therapists know the challenge is in setting the task. No motor learning happens if the task is too easy, because you've nothing to learn. If the task is set to be too difficult, you can't do it and you become demotivated. You have to set a task that has somebody at the pin of their collar working really hard to do that task. And that's where the learning occurs. And good therapists know this already. So again, apologies for very basic talk to therapists because they know this already. But when we're learning something and we're learning new motor strategies, you go through 3 essential stages: a very high cognitive element, where you have to give 100% of your attention, you make lots and lots of errors, and really you're just moving along through what's important for me to know to get this task done. Then you get to a stage where you can do the task to some degree, but you're making lots of errors. And it's really important, the error making in this phase, because here you're learning what's efficient and what isn't. And you're learning what's a good pattern and what isn't. And you're constantly refining till you get to the stage where it becomes automatic and you don't think about that movement anymore. It happens efficiently and effectively. Then you superimpose an acquired brain injury on that, and people are back down to what I call motor relearning. So they're relearning a task that was automatic to them before, and now it isn't anymore. And in that space, we are really asking people to identify from their previous patterns of movement what was good and effective, what can they access currently, and what do they need to relearn to get that movement back in any meaningful way. So then when we think about our acquired brain injury, here, because our physical interventions, our therapy are all physical and in the peripheries, but actually what we're targeting is the deficit in the brain and in the pattern of the brain and the ability of the brain to learn movement. And that's where we're really wanting to affect change. So we saw maybe the contracture is a secondary complication of spasticity, but your motor issues are a complication of a higher upper motor neuron lesion, which is at brain level. That's where the pathology is. And that's where ultimately our therapy has to target and make changes, positive neuroplastic changes at brain level to affect motor outcomes. And, you know, then when you're thinking about how do you present motor learning opportunities for positive brain plasticity, well, then the opportunity that you're presenting has to be challenging. And you only have to give the minimum amount of help to help that person achieve the task. And then we need to tailor the assistance as required. That's what we do in therapy, and that's what we need to be thinking about a little bit more in terms of robots and what they're doing with us and for us. And when we think about if any of us today, right here, right now, wanted to learn how to juggle 4 balls up into the air, we would be going through this, dropping them constantly, maybe getting one, thinking, oh, that one was good, so I'll remember that and I'll do it again. And we'd be keeping going. And as we're getting better, we're dropping less balls and moving on. Now, you wouldn't learn to be an expert juggler in a number of several hours, but if you're understanding motor learning at a brain level, in the first several seconds, you know, the brain is saying, I need everybody's attention here because I don't know what's important or not here in this motor learning task. So you can see all parts of the brain lit up here. We're all on high alert to know how to do this task. And then as we get a bit better, it says, right, these ones are helpful to me. So we're networking into these very helpful pieces of the brain that are telling us this successful pattern. And then when we get to the automatic stage, we're literally just saying, you know, network for this movement, active, please, because I only need you and you and you to do this movement well. Okay, and that's what we need to really be thinking about when we're training the brain. So we think about your acquired brain injury, you have a fundamental loss of motor stability. And we heard that in the previous talk. You can't really start thinking about the wrist until you can control the trunk and the scapula on the trunk in the first place. So here we have to think about motor stability and then moving into motor control, where we're looking at the task, we're looking at intersegmental coordination across multiple joints, and movement variability. They're very important components, and we need to be factoring those in to rehabilitative and robotic paradigms. Also then where I'm more interested perhaps is the neurophysiological level, where you do have sensory integration. So when you're up in a robot, you're getting lots of sensory input that's feeding back into the motor loop. You're getting a motor output, whether you're generating it or not, that's feeding back into the loop. And then what you really want to promote is this neural connectivity at brain level that's going to help to affect really positive changes. So then when we come from a bottom-up approach and say, well, we're trying to restore motor stability in acquired brain injury, well, then here is where we normally kind of come in with our exoskeleton type devices that give you a bit of stability. But then we have to have the motor learning strategies. It's not enough to be a passive passenger here. You have to be learning the motor strategy. And that's where we need the robots to be a little bit better than they currently are. This is a very simplistic model here, but just to show kind of where I started with this and what we need to know about it more. So at a very simple level, your brain develops the motor pattern, sends the electrical signals down the spinal cord, out into the peripheral nervous system, out to the muscles, and then to the muscle junction here, where our previous speaker was knocking out all activity with poisons. But here you come down to at brain level. So we need to be tracking at brain level what's happening. We need to be tracking at muscle level what's actually been executed from the initial pattern. And then we need to be looking really technically at the movement that's been executed, whether it's sit to stand, big functional movements is what I'm interested in, sit to stand, or stepping activity. So here in kind of a lab-based scenario, I'm looking at electrical muscle signals at brain level to see what's happening when you're executing a movement. I'm looking at the electrical activity at muscle level to see what's happening during the actuation of that movement. And I'm looking in our movement laboratory around the three-dimensional kinetics of the movement that was executed. And from this then, looking at seeing, again, using artificial intelligence mechanisms of modeling, can we effectively predict the motion trajectory? So if somebody is stepping forwards, can we actually, on a three-dimensional piece, use these neural biosignals to predict what they wanted to do? So that's what we asked first. And then can we develop really robust models, train them, here it is in stroke survivors, and then be able to deliver that back as a robotic command. So you have to execute the movement at brain level for the robot to do it. It's not enough for the robot to stand you up and walk you. And so this is what an EEG cap looks like. And just to show you, I have no vanity whatsoever because I don't mind showing you this picture of myself with a 64 electrode EEG cap on to really capture this in great detail at what's happening at brain level. So just to acknowledge that there's funding for two of these projects. The first project that I coordinate is called ProGate, and that's an EU-funded exchange program essentially that allowed me to bring together neurologists, engineers, and companies, one that makes an exoskeleton robotic device and one that makes wireless EEG and EMG signal trapping and signal processing. Again, the wireless is really important because we need to remove the artifacts associated with movement when we're really drilling down into these kind of signals. So we have 6 partners across the US, Italy, the UK, Ireland, and Austria. And we've been sending researchers and academics and people from industry on international and intersectoral placements to learn more about each other to advance this field, because we really need to understand more what's happening. I like to tell the engineers, you devise these devices because you can, and then you retrospectively fit them into a rehab setting, whereas you never ask the rehabilitationists what they wanted in the first place. I don't like this, this, and this about your device. So if you'd asked me, I could have told you that at the start. And say, for example, one of my colleagues up in Ulster University, Professor Damien Coyle, he's a brain-computer interface engineer. He does a lot of work in upper limb motion trajectory prediction, but he uses imagined movement. And he always says to me, well, why can't we use imagined lower limb movement? And I said, well, it's helpful when people can't move at all, but ultimately I want them to do. and you've got to do to learn how to do. So I don't want your imagined movement. I want real movement. I want people to have the pattern, execute it. I want to capture it, and I want it to go back into the robot. Now, this is a big task. I don't ask for a lot. The engineers love the upper limb because the upper limb motor cortex sits right up here and it's really accessible by EEG, whereas the lower limb sits down in the crevice between the two lobes and it's much harder to capture meaningful data. So the engineers love upper limb and nobody's really tasking the lower limb because it's much more difficult to do. Science Foundation Ireland now have funded another project that advances on this because we have preliminary data that we can work with. And this I've called the 3 R's, rehabilitative responsive robotics. And it is that looking at neurobio-signals, seeing if we can do these motion trajectory prediction models and see if we can actually entrain them in real time back into a robot. So just to show you a little bit of the first question, we had to go to basics here because we didn't have the answer from this in all of the scientific literature. Can you predict stepping movement using brain signals? So there's some evidence on treadmills. And again, the engineers had everybody on the treadmills because the treadmill meant that you didn't have to run wires up and down a gym, for example, when people were walking. But the treadmill has a very different neurophysiological pattern of gait at brain level and muscle level than overground walking does. And none of us ultimately walk over a treadmill during the course of our day, we walk over ground. So I wanted to come back and say, can you predict when somebody steps? So here we went into the movement laboratory. This is a secondee from Italy who came over to the Mater Hospital to do some work with us there, but he's modeling here in the lab. And we asked somebody just very simply to step forwards and step back, and we tracked the EEG signals as they did it. And here, if you look at the blue line, you can see when you start to step forwards, you'll see it moving, and then you start to step back. So here you can see that you can track very different brain activity during a step and during a step forward and back. Yep, so we can see here that we can pick up something that may be meaningful at brain level of what's happening when somebody is stepping. And again, the engineers, they look in all kinds of frequencies, alpha, beta, theta, low gamma, you name it, they like to look at it. I like to leave them at it myself. I think it's good practice. But nonetheless, what we are seeing is meaningful change and meaningful data that we can take. So here we have used that data now to look at the X plane of movement, so just forward movement, at the Y plane of movement, which is sideways movement, and on the Z plane of movement, which is up-down movement. And what we're seeing here is that certainly in the X plane, the forward trajectory of your stepping, we have pretty good accuracy. You can see that the red line is what actually is happening and the blue line is what we're modeling. So if we take these signals, we can interpret them in a way that allows us to predict with some degree of accuracy how much somebody is stepping forwards. Not so good on the Y and the Z plane, as you can see. It is tracking, but it's not tracking maybe accurately enough. But even to know how far somebody wanted to step or intended to step forwards would be really helpful to feed back into a robotic gait device. So can we accurately predict motion trajectory? We can do it pretty well, I have to say, much better than I would have thought in the forward plane of movement. And here I have a postdoctoral researcher working with me on this, and he's using artificial intelligence, machine learning, LTSM and CNN, the convoluted neural networks models to do this. And he's training these models and he's looking at the most optimal models. So this is the result of months of work of an engineer modeling essentially to get to this point. The next thing we did was, well, what happens when you walk in a robotic device? Just really basic questions first before we try and program anything. And here, as part of the project, we worked in the Mater Hospital, and we used healthy individuals. This is a healthy control walking here in the robot with the EEG on, EMG on, and then we had accelerometry data on the legs that allowed us to say when somebody was stepping and when they weren't stepping. And then we did the same with people who'd had a stroke. Here we used overground walking without an exoskeleton, and then what happens in the exoskeleton. And the results here were interesting, I think, and we need to think about this in more detail going forwards. But here we have healthy controls, and here you see at heel strike and toe off of the gait cycle, we're seeing really significant excitation at brain level for these 2 points in the gait cycle. So we can pick them out and we can read them from brain signals that these are happening. When we put healthy individuals into an overground exoskeleton walking, we are seeing other meaningful activity at brain level here. This is ERSP is what the engineers call this, but here we're seeing 2 hotspots, again related to heel strike and toe off of the gait signal, but they're different. So there's a different motor strategy being used to walk in an exoskeleton than there is to walk without an exoskeleton in healthy individuals. So you're learning a different way of walking. And that has implications in terms of what are you actually going to get as your final motor outcome. Then when we look at we had both right and left CVAs here, so we broke them down to look at them. And what we're seeing here is that in overground walking without an exoskeleton, we are not seeing the same cortical organization around stepping that we would expect to see. And when we put people into a robot to help them walk, we are not seeing that either. Okay, so it's not replicating walking, and it's not replicating robotic walking in healthy controls. So it's doing something slightly different. And we can pick up maybe 1 or 2 meaningful things along the way, but they are very different to what is usual in overground walking and what is usual to walking in an exoskeleton. This is work just coming in now from our colleagues in the University of Padua in Italy. And this again is healthy controls. So looking at the resting EEG patterns and then looking at them walking in an exoskeleton device and then looking at the resting EEG patterns again, what we're seeing is really highlighting here parietal, which would tell you more sensory type of stimulation, and occipital in terms of visual information, but we're seeing these parts of the brain are getting really stimulated and staying stimulated after exoskeleton walking. We're also seeing that when you ask people to walk after they've walked in an exoskeleton, they're using a much slower pattern and they're using much higher level of activity around their ankles for stability coming out of the device. So it's telling us a few interesting things. I guess it's important to ask people what they think about walking in a robotic device. So we did do that with people with acute stroke in the Mater Hospital. Overall, there was very positive feedback. They said you should go in with an open mind. Don't be put off by the device. It looks big and heavy and it isn't in reality. And they said things like, I think it's good because I wasn't able to move around. All I wanted to do was stay in bed, you know, and now I've made steps with this help. So when you can't walk, these are really, really useful devices. They said it's intimidating to look at because you don't think you'll be able to move in it. And then you realize that the weight of it, it's not as bad because it carries its own weight, essentially. They said it was crazy, but I enjoyed it. And then they also said, because here the therapist is trying to bring the patient with them in the gait cycle. So therapists give a lot of instruction, and they give instruction on weight transfer, and they give instruction on step now or step bigger or step forwards when people are using the active assisted mode. And they said, I think sometimes the instruction's hard to understand. Like I'm saying, move to the right, move to the left, that kind of thing. Sometimes it's hard, maybe less instruction. And over instruction is not helpful in motor learning. People need to recognize their own patterns, they need to recognize their own errors, and they need to take the corrective actions around it. So we have to be careful not to over instruct here. And if the device itself is more intuitive, that might be helpful. And this is very faint now. Apologies, it didn't come up as well as I would have liked it on the screen. But one of the things we did ask people was to rate how comfortable they thought the device was and how natural they thought their walking was in the device. And we looked here in maximum assistance mode. Here you're a passive passenger, and then in active assistance mode where you are actively contributing to your own stepping and walking. And what we found was that certainly in terms of the natural feel of walking, people with a higher modified Rankin scale of disability who were less able to walk rated the gait much more natural than people who had an ability to walk in some manner. So again, if you can't walk at all, being upright and walking feels natural. And we, you know, there's nice qualitative evidence from people with spinal cord injury that's complete, where they have no sensation from their lower limbs at all. And in one study I did, one of the gentlemen said, I know it's crazy because I can't feel my legs, but when I come out of the device, I feel connected to my legs once again in a way that I haven't before. So here we're seeing that when you can't walk, it feels natural to be up and walking. But when you can walk a bit, it doesn't feel as natural to be in a device that is dictating your stepping for you. And the same with comfort, because the more somebody could walk themselves, the less comfortable they found the adaptive assistance mode. So when they were trying to contribute to the device and the device was doing something else, they found that uncomfortable. And I've been in the device myself, and what I call fighting against the robot can be quite a significant battle when it is doing something that you're not. And so looking to the future, where are we going with artificial intelligence and robots? I think currently motion trajectory prediction is a lengthy process as we're doing it. It is conducted offline. We're getting better at predicting the stepping for sure. We have a challenge then to use neural biosignals in real time to program a robotic device. We'll have a challenge for people with acquired brain injury where the pathology is at brain level and the EEG signals are at brain level. But if we develop very good models, again, there's very nice work done in other fields of artificial intelligence that will recognize errors in models. Okay, so we can do that. They use it in the driving paradigms in artificial intelligence, and we could maybe adopt something like that in here. It's still likely that each model will need to be trained on an individual person by person basis, which would be a lengthy and time consuming process, I guess. But it will be high risk activity also to be in a device that is, you know, interpreting and deciding, say that you want to step when actually what you intended to do was sit down, and the consequences of the device stepping when you're sitting down could be potentially very dangerous. But the reward of having a responsive device is huge. So we need to be working a lot more in this field to move this along. So that's all I have to say for the morning. So I'm very happy to take any questions if anybody has them.
Thank you very much. I'm sure there are questions. I have tons of questions, but because we're using three different robotic devices here, and with a population that doesn't really have the the ability sometimes to give clear feedback on how they feel doing that. We also during the week visited the DCU exoskeleton lab and had what I thought was a very interesting experience, because we saw a person walking in the exoskeleton and then without the exoskeleton, and that was the question, well, if she can walk without it, why would she walk with it? And what you said, the way she walked was completely different. you know, in each case. And then the importance of learning to walk and to adapt your walking to the device rather than the device adapting, you know, to the way that you walk. So there's loads of interesting questions there that you raised, I think. But maybe somebody.
Thank you. Very impressive talk. I really liked it very much, and it brought actually a study back that we both did together. This was in looking at writing and learning writing tasks and using kinematic data of the tip of the pen, and looked at the way of learning a specific fast writing of 10 letters L. So we are all overlearned in that way. We can write very fast, and our movements are that way that we have a very fast movement in an upward stroke and a fast movement in the downward stroke, which ends up in a curve with only one velocity and acceleration change. And that's a high automatism. And therefore, my question to you would be,